So at this point, we understand what concurrency is, but what we really need to know is why do we need concurrency? On your computer, at any given time, you have hundreds of threads scheduled, and without concurrency, you'd need 100 CPU cores to run them. Now remember, a CPU may have one or more cores, and the core is that thing that performs tasks, and a thread is one such task. Now, obviously 100 cores is financially impractical. For example, my CPU has 14 cores. Typically, consumer machines have 4, 8, or 16. But even with 16, we can run 16 threads in parallel, but what about the remaining 84 threads? We see here in the image on the right, we have our 100 threads. We have 16 CPU cores. That accounts for 16 threads, but what about the other 84? Well, with concurrency and context switching, we can take care of this. We can schedule all 100 threads and handle them at the same time. And note, parallelism and concurrency coexist. Both are involved here because CPUs are resources that need to be shared. On the diagram on the right, we have time as our y-axis, and on the x-axis, we have our 4 CPU cores. And you'll notice that the tasks within a single core are never running in parallel, they're only running concurrently, but across all 4 cores, we're running various threads at the same time. So this illustrates the coexistence of parallelism and concurrency in how the CPU executes tasks. Let's take a look at an example. We have a GUI, a graphical user interface, and it needs to render the UI, draw the geometry and render everything to the user. And it needs to handle incoming network requests. This is 2 tasks that it needs to do at the same time. So say we're rendering the UI to the user and we're also listening on some open network sockets. If there's no incoming packets on the network socket, should we just block the program execution? And by block, I want to be clear, this would mean we don't render the UI whatsoever. The user just doesn't see anything painted to the screen. We're sitting here waiting for packets. Or should we go do something else, something better with our time, and come back later when we have new data coming in over the network socket? In fact, this is what GUI programs actually do. They tend to use a single main thread for drawing the UI, and then worker threads for these things like handling network requests. So takeaways from that example: concurrency is very useful when we have these pauses or waiting. If you're performing some sort of task that involves waiting around, like listening on a network socket for incoming packets, that is an ideal use case for concurrency. In the previous example, we should handle rendering the UI and receiving data over the network at the same time. We would use concurrent multi-threading for this. And here's a different example with worker threads. This is a very common example. A server, a web server that is, should handle multiple client connections concurrently. That means you have a web server, it's listening for connections. When someone connects to the web server, we create a new thread and we handle that connection in that thread. And then we have a one-to-one mapping between connected clients and threads running from the server. Now imagine a world where a server could not do any sort of concurrent processing. I do want to call out there is this thing called evented architecture and event loops. We'll touch on that toward the end of the series, but let's also imagine there's no real alternative. If we couldn't use concurrency, that would mean one client can be connected to the server at any given time. What this would look like would be you visiting a web page and finding that it is down because someone else is currently visiting the web page. Pretty unrealistic. So we need concurrency to be able to handle multiple client connections. The server handles each client connection again in a separate thread, and I've prepared a few code examples that we can look at that do precisely this. So this is our first example. This is part of the internals of an HTTP library that I wrote in C. This is the server that you use to create a REST client, and internally it uses threads. So here we have a main loop where we enter the loop and we wait for a new client connection. And when we have a new client connection, we spawn a thread. We make the thread a detached or daemon thread, which we'll talk about in, I believe, 2 videos from now. We also have what is called a thread pool. For now, all you really need to know about thread pools is it's basically a pool of a bunch of active threads that you can pick up and use and give tasks to, so you're not constantly creating new ones. But here we pass the client thread to this pool, and down here on line 257, we actually have the client thread handler. We've seen this before. This is just our thread handler. We have the void pointer return type and the void pointer argument type. We get this argument. This is context about the client request. Just a quick example. This is a pretty standard way for servers to run. You handle all of the client connections in separate threads. The second example is a bit more simple. It's a telnet chat server that I wrote also in C. And here you can see we create two different threads. This is very familiar from the previous example, so I won't delve into it too much, but we have our while loop. We get a client connection request, we register the client, and then we handle the client in a separate thread. But on line 718, we also create another thread. In this chat server, there's a concept of topics, kind of like chat rooms. You can create them. But if the creator has left the chat, we have a zombie chat room, basically a room hanging around with no owner. And so this is a thread that runs a routine, and periodically it checks for any hanging topics and removes them. So this is a worker thread. Again, this is a thread that just kind of runs in the background and performs some task periodically. It doesn't always have work to do, which is why it's great for concurrency, because we can handle the client connections in their threads, and we can also handle the main thread where we're running that primary loop and performing some other logic. And periodically, we'll context switch to this topic cleanup routine thread, and we'll check and see if there are any topics that need to be cleaned up. We'll iterate over them and remove them, and then we will context switch back to some client handler thread. So what are some takeaways from the examples that we looked at? We saw that worker threads are useful for computationally intensive and CPU-bound work. So in that latter example, we saw that we were looping, and as you know, iteration can be computationally intensive, especially if the max number of iterations is not bounded. Worker threads are also useful for non-overlapping tasks that may involve waiting and/or downtime, and they're not so ideal for file I/O or heavily overlapping tasks. Why might that be? Well, concurrent multi-threading can be unpredictable in terms of what order in which these threads will execute, and if you have overlapping tasks, that is, tasks that operate on the same data, that gets into the tricky territory of synchronization that we'll be spending quite a bit of time on in future videos. But for now, we want to be preferential to discrete units of work that could either be split up into smaller chunks or are simply non-overlapping. In our previous example, that was handling client connections and cleaning up topics. Those are two non-overlapping tasks. They have absolutely nothing to do with each other in terms of the state that they are touching on, but both of them can be computationally intensive and involve lots of waiting and downtime. That's it for today, folks. Make sure you like and subscribe because the next two videos are going to be about joinable threads and detached threads. Thanks for watching. See you next time.